Okay. Next question. What is the drift velocity for an 8 amp current going through a 14 gauge copper wire? Like this. Right, here's some standard house wire. We kind of like frayed this apart here. There we go, right? So we'll talk about why there's 3 wires in here later. This is normal house wire. There's 3. You see there's 3 on in the plugs also. We'll talk about that later. But let's just talk about for this one piece, we have an 8 amp current. What is the drift velocity here? So kind of what you might think here is you flip the switch, your light switch, maybe 8 amps go through your house wires. That's a normal amount if you have a lot of lights. They're the outdoor Christmas lights, so it's a lot. And then the drift velocity, at what rate are those electrons on average drifting through the wire, right? And I put some information, right? Copper has a free electron density of 8.5 times 10 to the 28 electrons per meter cubed. And 12 gauge wire has a diameter of 2.06 millimeters. 14 gauge wire has a diameter of 1.63 millimeters, right? Kind of going that weird system of smaller is bigger. But we're 14 gauge, so we will go with that 1.63. And let's pull up a formula that we had from last time. We kind of ended here. Electrical current, negative E, free electron density, area, drift velocity. Well, I think we know I is 8 amps. E is something we look up. NE is that number I gave us. Every material is different. I just, you never have to figure it out in this class. But it just depends on the material. So we have that value. It's given. A, area of the wire. Well, if we have the diameter of the wire, I think we can use some geometry to find the area of the wire. So let's kind of write down this formula that we have here. We'll say I equals negative E NE A V D, right? Just copying that from before. Let's solve for VD. Just divide by all that stuff. That's what we're solving for. VD equals I over negative E N E A. Right, so all I did was I solved for drift velocity. Now let's just list these constants over here. I is 8 amps, we know that. Amps is the unit for electrical current. It's coulombs per second. I'll add that here. Amps is C over S. E is the charge of the electron, we know is 1.6 times 10 to the minus 19 coulombs. NE was given. It was that 8.5 times 10 to the 28 electrons per meter cubed. And now we need to find area. Right, I'll just kind of show what we looked at. 8 amps, 8 coulombs per second. There's that charge of the electron. NE was given. And now area, if it's a circular wire, I don't know if you can tell, the wires looks pretty circular. Ooh, maybe you can see on that one. I don't know. Pi r squared. I think it's going to be pi r squared, which is pi times d over 2. Oh, well, let's see. 14 gauge, 1.63 divided by 2 is 0.815 millimeters. So divide that by 1,000. 8.15 times 10 to the minus 14. No, minus 4. I don't know where I set that for. Right, and so then that area, we just plug that into our calculator. Pi times answer squared. Right, that's the cross-sectional area in meters. It's 2.1 times 10 to the minus 6 meters squared. Cool. So we have all of our stuff. We have A, N, E, E, I. We can just plug those all into this formula here. And let's see what we get. So let's see. 8 amps divided by 1.6 times 10 to the minus 19 times 8.5 times 10 to the 28 times 2.1 times 10 to the minus 6. Ooh, I got 2.8 times 10 to the minus 4. Minus 4, and that's going to be meters per second, which is equal to, I'll let you do the unit conversion, 0.28 millimeters per second. Seems reasonable there, at least the unit conversion. So I got 2.8 times 10 to the minus 4 meters per second, 0.28 millimeters per second. So let's think about what happens. I flip the switch, off. Then I flip the switch on. Okay, there's an alternating current actually in the wire. Let's ignore that for now. But how long is it from that switch to that lamp over there? Probably at least a couple meters. But we said the drift velocity is 0.28 millimeters per second. That's much slower than what we thought. And the reason why it's slower, you might think, wow, how did the switch turn on when the electrons are moving so slow? Think of it like, I think of it as toothpaste. If I squeeze the back end of the toothpaste, and I just do it slowly, the toothpaste might be going at 0.28 millimeters per second. However, immediately, the second I squeeze one end, toothpaste comes out the other end. So that drift velocity is not the same as maybe we would say the response speed of the electrons in the wire, right? So they start moving at that slow rate. It takes a long time for them to get from the light switch to the lamp, kind of on average. But their response is much quicker than that 0.28 millimeters per second. Cool.